All right, well, let's get back to yesterday's lecture. So yesterday's lecture, we were talking about the bus structure to get data from point A to point B. We went through this diagram, or this example, where we were trying to take assembly code, looking at the addresses of your two devices and trying to predict what the bus structures and what the bus signals were going to be. Okay, so you guys went through that. Great. And now what we're going to do is think about if you are the, what's it called, the requester and completer, your job is to write a completer, write that digital logic such that your peripheral, because a completer is a peripheral, is able to complete some tasks. So say we want to control the lowest significant bit of a register. So a register here is like a 32-bit set of D flip-flops. We'll just designate this as a D flip-flop, but we're going to show that it has more than one by this nomenclature here. So here's showing the concatenation, and then we have the label 32 bits. And so we can say, well, what are the conditions in which this thing should respond? Well, the device, the peripheral, should be selected. It should be enabled. And if you're trying to use the lowest significant bit of to control the LED, that means it's an output. It would have to be right as well. So those things all have to be true. And then you could enable the D flip-flop. Now, there's other circuits that could be done. We're just talking about the circuit that, we're just showing an example here. Here we have 32 bits coming into this 32-bit register, but we only really need to look at the lowest bit. And so here it's just said for the LSB, so I'm just showing you the LSB. There should be a marker here, a denotation. Yes, there we go. So this is saying this is the 0th line here. So this would be a bus, or this is a bus structure. This is just denoting this is the 0th of that output pin. That goes to an LED. And we have a P clock and a P write. Now we didn't do any address masking. We can just assume that this is the only register in this completer or in this peripheral. So this, if you had a statement that would store data, a 1 or a 0, into the lowest bit of this address, which just happens to be the only thing on the select line, then the LED would be raised and lowered. What questions do we have? Yeah.
Are we still sending all 32 bits through Q, but we're only looking at the last?
Yeah, you could have rewritten this as one. There's lots of ways to do it, right? This is a toy example. You could have had one flip-flop and then take the 0th line off of the data bit and store that there. What other questions do we have? Yeah.
I don't know if that's maybe I didn't this up, but we were reading, we use Q and feedback to.
Yeah, we'll go through a read example, but yes, there's different functionalities. We're just trying to show what's the minimum number of circuits to make an LED turn on using this interface. It's not the most complete completer possible or most robust one. Yes?
Can you explain what the notation is for P ready?
The notation for?
P ready on the very bottom.
Oh, this is a power symbol. This means VDD. There's a logical 1. That's a logical 0. That's ground. And so here, that's a great point. This is just saying that P ready will be ready immediately. If we look at our timing diagram, here we see data came in. It was a logic. It doesn't matter what the uppers were, but the lowest bit was something. And then P ready was high immediately. There was no reason for it to wait because this was clocked in immediately when it was available. The peripheral didn't need to do tasks before turning on the LED. Okay, so we can kind of expand upon this example a little bit. What happens if you want to write to multiple registers in one peripheral? This is the normal case. And your GPIO registers or peripherals, there's multiple registers. So here we have register A, register B. And we have, the note says here, here's the addresses for which these respond. Okay? And so how would we do this? Well, you'd have to be writing, so writing is going to be high. The whole thing has to be enabled, and p-select has to go high. Okay, those things have to be true for any action to occur. And the action is just clocking in data. Here we've done some wild notation. So we have an 8-bit bus. This is the P address bus. We just said it was 8-bit for these examples because I don't want to write out 32. It would be too many. And then we just use an AND gate an AND gate with bubble logic here, or AND gate with bubble logic showing that we're going to take the inverse of this, and then here we've denoted that it's going to be the fourth, number 4. So here this will go high if you get 1, 0, 0, 0, and this will go high if it's 1, 0, 0, 4. So that's just a way to select. Then what would we have? We're going to AND. So if the address is 1000 and all these conditions are met, then this register is turned on. So here is like the combinational logic. That's why those diagrams, the completer was a bunch of combinational logic to get some tasks done. So all those things have enabled that. Likewise, we can take, let's see, the output of this and the output of this to enable this device. So far, if this is true, this is true, this is true, this is true, then you have turned on one of those two things. Okay. And then to complete it, you got to actually send the data. So now the data comes off the data bus. This is 32 bits wide. And now it's being passed to both of those. And then what is next? Yeah, P clock goes to everything. And then data ready is held high immediately because you clock the data in immediately. We're not talking about reads. We're not talking about anything else. Just the brief was, how do I write to multiple registers? This is how you could write the combinational logic to achieve that task. Yeah.
So why does P-ready not connected to? No, sorry. Why does P-ready not connected?
Why is P ready not connected to anything? It's connected to high. This is a power symbol. It doesn't need to, because the registers will complete this task immediately on the falling edge. Let's see, when P enable goes, let's see, let's see, P enable's high on this clock edge, right? This clock edge will latch in all the information from data, wherever data is here, right? So all those conditions are true at this point. And so it doesn't actually, and because it happens instantaneously or close to, we don't have to hold this line low for a period of time. So we're just going to say it is high. We'll talk about wait states where we actually do have to pull this thing low later. Yeah. Really loud.
Writing to a specific address, or just the one?
No, the last one we just said the only destination here. This is the only register on all of all that completer or that peripheral. So P select will do the job of selecting. The most robust thing to do would have had to mask for AND. In fact, if you were at ARM and you try and draw, Professor Sample's goofy diagrams, they'll laugh at you. They'll say, no, that's not robust enough. We have a whole combinational logic suite to do the most, robust thing. But this is just the minimal amount of circuitry required to accomplish that task. That's why we're showing you that. Okay. Yes?
Ready is connected to the power source. What is it, the power source?
So these are combinational logics. Inside the D flip-flop, there's a line to power. So this is on the chip. I don't know. I think the STMs actually run at 3.3 volts. So they have a power line throughout the entire chip, and this is available to be tapped into. And power BDD is just the same as logical 1. Okay, what about P write data? What happens when you want to write data into this, or read, sorry, this is P read data, write data. This is when you want to read data out. Okay. And also remember that each peripheral or completer has its own data bus. That was going back to that diagram. We saw all the yellow wires coming back. All right, so we can talk. I don't know why I inherited this slide with Mr. Switch on it, but this year it has Mr. Switch on it, okay? Looks a little goofy. But here's the goal. We're trying to take an input, so this would just be a push button, and we're trying to get that into that piece of hardware. So regardless, there's no GPIO pins. Let's ignore that for a fact. But there would be a logical 1 or 0 coming out of this device, and we're going to capture it with a D flip-flop. Notice that I've switched the Q and the D here to make it confusing for everyone. But you could imagine that On the clock edge, this signal will be either high or low, and it will be latched into this DFF and then be made available on a D read line. So here the core is reading out of this memory location. And we're just going to denote that here's the 0th bit of this. You would have, if you wanted to have 32 of them, you could. And then they could go to 32 different switches. In this example, we just have one button, and then we just arbitrarily chosen as the 0th bit, but it can't be all 32 bits. You need a clock. This thing is ready, available, or immediately. What questions do you have? Yeah?
Is it possible that something's not ready immediately?
Yes, we'll go over that example. That is the typical case. If you're just reading in and out of registers, they want to make it fast, so that's immediately available. But say you want to do something complicated like an ADC read, an analog to digital conversion. You say, take your analog, start the conversion, and send me back the value. Well, it may take up to 16 to 32 cycles before that thing gets completed. And that's, well, I mean, it's a small detail. As you'll find out later, the clock on your peripherals is usually much, much slower than the clock of your core. So now, because you also have different timings, the peripherals are generally waiting from the core's point of view. Yeah?
Do you have like it takes a long time to read from? Does the entire browser just like stall?
It could. It depends how the code's been written and how it's been optimized. But yeah, these processors don't necessarily have, they're not sophisticated enough to have an automatic way to take care of that. The way we end up taking care about it, you'll learn about later, is you tell that peripheral to interrupt you, to set an interrupt when the job is done. So an interrupt is just a signal that goes back to the core that says, hey, I'm done with a task, and it's asynchronous of the bus structure. So there's a mechanism, it's just not, there's no queue or multitasking or anything inside these things. Okay, so there's one problem with this, and we used to be a larger problem when we had an older lab type kit, but for button reads it's not that big a problem now, but students will eventually run into this, so we just bring it up. And that is this idea of metastability. That is so here we have a bit that's transitioning from 0 to 1, and here is different latch points. And so what they found out is that if you were trying to latch in a signal when it's halfway between 1 and 0, there is non-deterministic which way it's going to go. Sometimes you can even get the thing locked halfway in between. And that's the worst case, but other times it will get latched in and it will be undeterministic for a while, and eventually it will propagate through the system. So typically they say, well, you don't just be careful about having asynchronous systems. So that's the real story. If you have two systems on two different clocks, there's no guarantee that the data is perfectly ready. And if the data is within the 50% range or close to it, you don't know what's going to happen. And so the way around that is that you put two D flip-flops in series with each other, and the likelihood that it breaks or has an issue with one D flip-flop is low, but still there. But the likelihood that error will propagate to the second D flip-flop is very low. So that's the way they get around it. You have an input, you don't want this metastable state, this metastable meaning between two states, propagating and corrupting your system, so they put 2D flip-flops. But that's not good enough for medical systems. Medical people say we need to have 3D flip-flops. And then the statistics say that's about the life of the universe. That is how likely that a metastability event will occur through two D flip-flops. One D flip-flop you can demonstrate in the lab pretty easily. So what you have to learn, I said a lot of stuff, don't learn anything. Only thing you're supposed to learn from this is that if you have two asynchronous systems, you should worry that you're clocking data in the middle of the transition, and the way to get around that is 2D flip-flops. There it is. Okay, so then you can modify this example to overcome this issue by putting 2D flip-flops, and then this person, because some guys are pointing out the problems here, you wouldn't be immediately available, you have to wait an extra clock cycle for D to go to Q and D to be available on the second one, and so in that case, you'd have to go put in some sort of delay circuit. So I drew a crude one here and just grayed out clock to make it a little bit more readable. Essentially, when this thing is enabled, right, then it will delay by one clock cycle by feeding Q back through, and then it will lower P ready it'll lower it for one cycle and then let it back up. So you'd have to have some delay structure here. Yeah.
How come with the data like between like it being I guess unknown to data one, like when the address becomes available, but you're not certain what you're reading yet, like where you data one.
Wait, you want to go back? Oh, here?
PR data.
PR data, yeah.
And the timing diagram.
Yep.
How come you can't with that delay in the data compared to when you can see the address right away?
Because this is the read data. This is the data coming from the device. And we're just saying that it was unknown or undefined there. It wasn't ready until this thing, this is what the circuit diagram from the manufacturer is saying. It doesn't matter what the data was. Could have been anything. It's undefined until P-ready goes high. And the only reason P-ready goes high is when all these other signals go. Then it has opportunity to go high, and that is when the data is valid. It could be ready for a long time beforehand. And then I made a mistake. I don't know why I lost it, but this one should have a separate D flip-flop there. So I'll update the slides to put 2 D flip-flops to match the problem. So I was trying to solve this problem here by adding a flip-flop here, but then somehow magically through the, I don't know, through magic, I lost that D flip-flop. So there should be 2 up there to resolve that case. Okay, so let's move forward. Then we can have one more condition. What if you want to read between 2 different switches? And we'll just make it a simpler case. We don't worry about metastability for a second. In this case, we say, okay, we have to be able to select. Well, how would you select? Well, let's use address. We'll use the second bit in address to control which one of these is going to, because you could use any bit, but you can use the second bit here to control these 2 pins. Oh, no, this says if I read from this address, A, then I want to get from switch A, and if I read from this address, I want to get switch B. So here, now I remember why I put a 2 here. So by putting the correct address on here, the second bit will go and select this thing and switch the mux to one of these 2 D flip-flops, and then you can read it out. I see some confused faces. Many confused students. Fantastic, a brave student.
It says there's only 2 bits being read from the P address.
It says? Yeah, well, it only needs this bit. All the other bits are don't care. Right? Because I'm just trying to select between this and here. And why did I choose that? Because I'm trying to go between this address and that address. So what's the bit that differentiates between those addresses?
First one. The 0 and the
No, this is the address. I got to go 1004. Oh, I guess we should have said that I guess I should have put a caveat that this entire register, a peripheral, is a register 1000. And then that would enable P-select would have enabled it. And then this would be the second bit. Okay, so let's go over some notation and we'll have you all have a practice at this. So notation here typically is, you have 2 different types of flip-flops. You can always add in or remove as many enables or resets as you want. Those are fine, but you have to define if it's 32 bits or just 1. You can use to select an address. Sometimes it's really horrible to write bubble logic. You don't like it, I don't like reading it. So you could just write down, here's an add or mask, this is the thing I'm supposed to be masking for, especially if it's an exam or something, and we're saying like, you, instead of writing out all the bubbles, you just write down what you want it to be. If you have a bus, you should tell us how many number of lines are in the bus, and then you should tell us what the concatenation is. So here's the number, if you have brackets, that was gonna tell us this is a 32, and then here's the upper 16 and the lower 16. And then, as always, VDD is logical 1 here, and ground is logical 0. Okay. So you guys should have a worksheet. Your goal is to connect up this register in this peripheral such that it reads from all registers and it writes to all registers. And if anybody doesn't have a worksheet, let me know. So this should be 4.2. 3. That's 5. All right. Does anybody have any extra worksheets? 4.2 worksheets? Number 5. There's 4.2.
There's one extra.
Same, but we would just have that medicine relay thing.
2, yeah.
But I don't think we're doing anything synchronous until
Does anybody else? You need a worksheet. Fantastic.
So right for that.
All right. That's fine. I gave everybody lots of things.
You need to read the alphabet. Yes.
Here, I'll take your extra 5 in case somebody needs it. All right.
Okay, nothing to the.
It's value for read.
read it when it's not being able. I cannot write it. So and being able for
U goes to
selecting these two.
like U and the enable.
Right, it is gonna go.
Right goes to D.
Specific register. Ready.
Let's select our enable probably needs to be ended with this select.
I don't know what you're right. No.
Data's coming up.
Yeah, sure.
That's the correct approach at all. I'm confused. I don't really know what we do for P editor.
Okay, you have any course?
I'm pretty sure I've seen D, you know?
Diagram.
Maybe too high or something. I don't know. Read the diagram. Yeah.
There's nowhere.
Look at the graph.
Does anybody have any lecture 4 worksheets?
P adder selected which register to write to. P cell, P enable, and P write are all
Yeah, we have to add piece.
Some of these just doesn't even
I think he ready.
all reads, so we should do nothing.
Yes, it's a line.
Address, but for the other ones.
What else do we have to do?
So if it's like, yeah, wrong or right?
That's data. You write data, it's going to be.
Just writing it all in the clockwork.
Then I think this addresses.
Well, that looks all good to me.
The right register.
This is the actual. We use that, right?
Enable P right and then that whole thing is
P into enable.
But if you do a write,
That was P select.
and it's updating what it is.
So I just don't think we use it because the address doesn't matter.
It says all read.
Looks good.
We just wanna. No.
Yeah, I think.
All right from the register. So I guess there's no address. Address.
P right or yeah, P right should be ended with
That's it. We're reading from this one. Apparently, there's only one register.
When it's enabled. So
That's what I was doing.
Yeah, we and all 4 of them.
yeah, but I didn't go to my strong.
Yeah, no, but I did. Not this one.
All right, are we ready?
You're supposed to be.
If we want to,
You ready? You guys to PPE?
right, to have it do a task, what are the pins that have to go high to enable actions like reading and writing? Yeah. So we can collect those to enable. Now, even if the write is down, the data is always available on that bus. So we can go here, we can, OP select. So if write is low, then this line is not going high. However, enable only updates. Enable allows clock to update the DFF based on D. So if this is deasserted, it doesn't matter, the data here isn't changing, clock keeps spinning, but the Q data is always available, right? And remember, each individual peripheral has its own bus back to the core, or back to the requester. So it doesn't matter that there's data on this, we don't have to mask it out. We only care that these things are all high when we're trying to put new data into this. Okay? So that's the way we're gonna select whether we're allowing data to come in or holding data. We didn't really care about address. It could have been, I could have given you an address, maybe I should have given you an address for the example, but if there was an address, then you could put an adder mask and write down the address here or do the bubble logic and then and that into this line as well so that this thing would only update when it's being written to the proper address. And then here we have data is always ready because this happens on T3 no matter what. There's no extra delay. What questions do we got? Yes?
Okay, why does
You have to be loud.
write, enable, and select go through an AND gate and not?
Because it's not, all of those have to be true. It can't just be one. If we look at this timing diagram, it has to be, all of those have to be high. It can't just be just one. Why can't it be one? Because P-enable goes to all peripherals. And then you'd be tricking the other peripherals would be on and trying to act. Yes?
The clock.
Oh, that's just the clock symbol. I don't know.
Oh, okay.
It's like some EEs from the 50s figured that out and put it there. I don't know what it means. Yeah.
Shouldn't there be some logic to P ready because like on T2
You ready? Gosh, this is just denoting that it's in either state, it doesn't matter. This is the only time it matters. That's what the nomenclature means. Yeah.
For P write data and P read data, are the double lines, are those just signifying that it's a bus that could go either way?
Yes.
Okay.
This is the bus, and then we gave you the second hint here that's a 32-bit bus. One more, yeah.
Data in a 32-bit bus structure.
Additional information for read data based on addresses because we don't know where they're going
To like which specific address.
That's true, maybe, except for the fact I made a toy problem for you. And the toy problem is this is the only thing in this peripheral. And there's a bus that goes all the way back to the requester, and each peripheral has its own bus. So now it's the requester's job to look at the correct bus. So it's not corrupting anything else by doing that. One last one. Oh, you got a good question, okay.
So would we be penalized on the exam if we don't like draw double lines?
No, because God, drawing things are horrible. Just try your best and use all this bus notation if you can. This will really help me because there's no way you're drawing bubble lines, but you can do a little slash and indicate that it's 32 bits and that will help out. On the exam, we're trying to help, we're hoping you get close. Perfection is great. We all love perfection, but I want you to actually teach me that you know what's going on and I don't need perfection for that. Okay. Let's see. So a write transfer with wait states. Let's go through an example here. So what does that mean? Here, we have the setup phase. Then ready has been pulled high, remains low, saying that the data is not ready. So it's held for 2, and then they go through the access phase. So normally it's setup, access, setup, access. Here it's setup, wait, access. Okay? Let's talk about that condition. And then if you're going to read data, the same thing could be true. Do I have animations? I don't know. I have 2 wait states here. And here we're just saying the data is unknown. Why is the data unknown? Well, the peripheral has been asked to do a task, maybe do an ADC conversion or do some timing task. And the data is not valid. That's why they're showing it here. It's only valid when it's been set up in the access phase. This thing goes high, telling the requester, hey, look, the data is valid now. Now is your time to clock it out at T5.
What would a P-ready be wired to here?
Well, it could be some wacko circuit that I drew over here just before class. So here's the circuit that's going to cause the delay. You'll see, like on the exams, typically there's like some external device that you're like connecting to, and that thing has like an enable pin, or sorry, a data ready pin, and then that would have to go through here. What else I want to teach you? If you get confused, mildly with my lectures, that's pretty easy. The data sheet for the APB bus is actually pretty good. 100 pages, pretty readable. just walk yourself through the state diagram. This is what the logic of those lines are supposed to be accomplishing. And it'll tell you what happens when there's a transfer, what happens when there's a P-ready's not available. Work your way through this, there's another way to think about it. There's some things we left out, like P error, and there's a bunch of other lines that are really not, I mean, they're important, I suppose, but they're not valuable for you to learn how buses work on chip. So if you look through the spec, don't worry about some of those extra data lines. But there is a full list if you need. Okay, so before we move on to the next lecture, what questions do you have?
Is the access phase only when P ready is high, and it has to be after the setup phase?
Correct. Yep. So every interaction takes at least 2 clock cycles, right? Because you got to set up and then you got to have the access phase. All right. So here we're going to try and put it all together for you. All right. So today we're going to talk about GPIO pins and methods for driving pins, and then we're going to do another example of trying to get the APB bus to a GPIO. All right. So far we've been talking about we have a core. Inside the core is this memory interface. That memory interface is essentially the requester. However, there's the advanced peripheral bus, and when I teach you things, it's the requester that's in here, but for the purposes of this class, we'll just assume this module is in here. Anyways, let's assume the module, the requester is in the core. It makes things a lot easier. And the goal is to get data throughout the system. So here, right, I want to go talk to a register bank, so I'm doing a store or a load, and I have to get data into or out of a GPIO pin. And again, those are peripherals. So one thing I want you guys to realize is that this whole core, all that diagram is on a piece of silicon. It's on a chip, okay? And you're pushing data in and around this chip. So for example, this is we call chips, integrated circuits. This happens to be STM32, a smaller chip than the one you guys use, but still from the same family. And in this case, we have the core here, we have a bus structure, and we're trying to get data out to a pin. So everything we've done so far is how do we get data to that pin. These pins, this is a chip and this is a package. So this is a package, and then there's wire bond. So there's a special machine that you need gold wires to be able to connect to silicon substrates. There's a little bit of chemistry involved that I don't really understand anymore. But then you use your wire bond machine to go to these metal things here. These are pins. And the reason that you have, they're black is that they have to be insensitive to UV. You don't want UV hitting your chip or else you get bit flips. And this mechanically keeps it safe. All right, so now we're going to go and take that pin. It's going to go, the data from here is going to go out to that pin. And then this package sits on a PCB. Okay? And this pin is what you're usually hooking up to your oscilloscope or some LED or something. I don't know if it's exactly that one, but the traces go through here. So this is literally that block diagram. There's a core pushing data through here, makes it all the way out to your device. Does that help? Now let's just talk about one of these GPIO pins here. Okay? So here we have a general purpose input-output. Here's the example, that pin crossing from silicon onto your PCB, right? So what's connected to it? Well, you have an input register. So data can come in from that pin and be held in the D flip-flop to the, in our case for this chip, is the high performance bus, but it doesn't really matter for the purpose of this class. You can take data in to this bit and it can go out and be put out in that pin, but you need some control logic. This control logic is going to disconnect this thing from this pin or put it back on. So if you're doing an input, you don't want this thing pushing out at the same time. You need to have some digital logic here to control that, and you need a method to control it. So that's why you have a control register. So here now we have a control register that sets the direction of the pin. Is the pin an input, meaning it's updating data, or is it an output, meaning data is being put out here? Okay, so now we have 3 registers. We take those 3 registers and we start concatenating them. So here we're going to call them that, say that's port B, pin 0, 1, 2, 3, and now we have your whole GPIO port, right? Multiple pins, multiple LEDs can be turned on and off. Inside those, we have all our input registers can be concatenated together. Remember, they're all put together, they're on there, so we can go and put them into a register. We're gonna give that register an address. It's gonna look just like memory. We can do the same thing with the output registers, assume that they're all been highlighted underneath. And we have the control register, and we're gonna concatenate them all together and give them an address. How are we doing? Questions? Brave people with questions?
So, like, is the control a matter of saying like user output?
That's it for now.
Or is it like use the input, like make the input 1 or 0 with the controller, or just like use the input or output?
Control tells you if the output register is connected to this GPIO pin, or do you want the GPIO pin connected to the input register? Okay. Now we have registers with addresses. Fancy animation time, here we go. Move away some of those things. And now, this is just memory. In fact, I'll even change the notation here. Instead of calling them registers, we're gonna call them memory. And from the core's point of view, the core doesn't care. The core is like, this is just memory, it's got addresses, I'm gonna flip those bits up and down. And you know how to do that. You guys are great at it now. You do loads and stores. Loads and stores manipulate bits. I'm gonna do loads and stores, I'm gonna manipulate these bits, and these pins are gonna go high or low. And how are you gonna do that? What's the mechanism? Well, that's what we did learning about the bus. So here we have a processor, we have the requester. Those are inside the Cortex-M core. They transport the data across here to the completer. The completer is a peripheral. Okay? So here you have the completer, you have this register, and all this sort of stuff is in there. And then to send data through, you're gonna say, okay, I'm gonna execute this instruction. Data is gonna go through here, come through out here, and it's gonna manipulate one of those registers. One of those registers, remember this little bit here represents one of those things, and now I can control these registers and be putting data in and out. Too many blank stares. This is great. This is exciting stuff here, I promise you.
What kind of memory is the GPIO peripheral relating to?
Is the GPIO peripheral?
Are those just flip-flops?
Yeah. Yep. You wouldn't want to use SRAM, it's too dense, it's not the right structure, so almost all the time in the peripheral it's just going to be a flip-flop. Now it is up to the hardware designer, I don't know, they could use JK flops, I don't know, but generally it's just going to be a D flip-flop. Yeah.
So where's the output control? Is it output control?
Right here.
Yeah, is it in the GPIO?
I mean, these two blocks are inside of here, maybe we put this one right here. But yes, they're all in the peripheral. You have a completer, which is that digital logic, that state machine we were drawing before, and you're like, why do we have to worry about D flip-flops, and you're drawing circuits? You were drawing this, it manipulates registers, those registers manipulate GPIO pins, or whatever your peripheral is. Loud.
The memory diagram is a singular square indicating one register.
Yeah, in this diagram. Yep.
Would it be correct to say that the state machine on the requester side of things would be the implementation of that like long memory diagram that we have with all the different like points in memory so it knows where to go, or is that like unrelated?
It's related. That memory diagram, remember the one where they had lots of reserves and it was very confusing because like why did ARM lay it out and then the STM and all the manufacturers do whatever they want anyways? That is baked into these addresses. So we're going to say that you can only write to addresses that are not in the reserve space, that are in the peripheral space, and those addresses represent these registers right here, the state holding elements that are inside your device.
Even though we have like address from the processor and address from the GPIO peripherals, they're essentially from the same like big block of addresses.
Yeah. I had an animation at one point where we had all the different peripheral, like all the memory blocks, and we distributed them throughout. So the core doesn't know that they're distributed, right? The core just thinks, okay, I have memory address F, 0 to F, whatever it is, 4 gigabytes I can write to. It just happens to be some of those represent different things. Some of them will represent FRAM or SRAM, some will represent flash, some will represent these registers. Any more questions? Okay. right? So I think this is probably the crux of the first half of this class. This is exam 1 essentially, right? Like understanding how data flows through here. This data is going to cause these lines to go high and low. Which of these lines are going to go high and low when you do this, right? These lines go high or low causes bits over here to go high or low and control some things, some tasks. Typically, you guys are writing some sort of state machine here, or some combinational logic which manipulates something that will talk to the external world. Yeah.
So the output register are taking information from the pin, like, so you write to the output register by using information from the pin, right?
You write to the output register. Well, the output register is sensing like, it says the output register here is the output pushing data out. So you're going to put a store command that's going to put a logical 1 in here or a 0, and that's going to translate to raising this pin high or low.
Output to write, and then input to read.
Yeah. And it's always important to think about whose perspective are we talking about. So, like, right, if I set the GPIO pin to output, that means this pin here can either drive this signal line high or low. It will drive it high. If it's an input, then it's going to sample this pin, measuring if it's high or low, and then report that into a register which can be read by the core. Yeah.
In the lab, we configured the output type to be like push-pull or something else.
Yep. We'll talk about that in a second.
Okay.
It's a good question.
Do the control lines point to multiple computers?
What's that?
Is there like multiple computers?
Yes.
Like, the select points to like a lot of things. Is the control lines point to like multiple completers, or is it like the completer points to like, or like once you have the completer, the P select points to different P flip flops?
Let me see if I can reinterpret your question. Your statement is, what happens if there's multiple of these things, right? There are lots of these. There's probably at least 64 on your device, okay? That means one of the control lines, which I didn't draw them all out here, is P select. P select is going to select one of those 64 peripherals, okay? Inside that peripheral, there are going to be registers, multiple registers. Those registers have addresses. So first what you do is you say one of those 64 peripherals, I'm going to select you. And then it gives address pins. It tells you this is the address inside the peripheral I want you to read.
So there's one requester.
Correct.
And there's like a ton of completers.
Correct.
And they all get the P select to know which one of them is being chosen for the job. Okay.
Yeah. And so the thing you don't have to know, so you can turn off your brains, but the reason why they have P select and address lines is they don't want to actually put 32 address lines. That would just be too many. If you have 64 completers and say there's only 32 registers in any one completer, then you only need whatever that is, 8 bits to address any of the registers inside a completer. So the goal is P select allows you to reduce the amount of data lines you need for address. I wouldn't worry about it too much for an exam to know that little detail, but that's why they do it. Yeah.
I've got 2 questions here. One, just in the diagram, those blue boxes on the right side and those colored boxes up there, those are the same thing, basically, they're all registers?
Okay. Yeah. It's just, one is like a circuit diagram representation. One is the memory representation. So when you're like, this is different representations of the same thing.
Okay, got you. Then second question, let's say the requester tries to access like the 33rd register that doesn't exist.
Yeah.
What would happen in that case? Would it just wrap around to like growth or first register, or would that cause a fault of some kind?
So this is like the error condition that's built into the hardware. So first, your compiler shouldn't let you. So QBID should say, hey, that's out of bounds. And if you do try to read from it, it's likely you're going to get nothing because your row and column decoders, if you're trying to look at a memory address thing, it will point to something that's invalid. So it'll probably give you back zeros or ones or undeterministic. In fact, a lot of times in your data sheet, it will say if you do this task, it's undefined because they don't know what will happen. All right. So let's talk about what's inside these. Let's go to the next step and talk about what's inside GPIO pins. A little bit more detail. I gave you a cartoon version. let's try and get to another level of accuracy. So this is from, yes, it is from the data sheet. You can go look it up for your particular chip. And so here they have these push-pull types that we were talking about. You have, let's see, you have write, you have read registers, you have, oh, these are, so this is output data register. It's telling you can read or write to the output data register. So say you made a pin high, you forget that you did it high, you can still read the data out. It doesn't mean you can get data from this register. We didn't show that as a diagram previously. So these are read write. You can only read from an input register. You can't put data in it. It won't allow you. And then you have your select registers. And then there's this thing here we'll talk about later, alternative function. A lot of your GPIO pins, because there's not that many of them, so they're going to be input output pins or some other pins. And there's an alternate path to get data in here. These are push pulls, and then there's a Schmidt trigger. Interestingly enough, they have diodes, or sorry, they have protection diodes. These are pretty cool in the sense that if you have over voltage, right? If this pin raises higher than VDD by 0.3 volts, then it'll start conducting. Likewise, if this one pin is lower than ground by 0.3 volts, it'll start conducting. So I actually had an error condition in one research project where I was doing some weird energy harvesting, and all of a sudden the clock would go wild. The clock would start increasing and going faster and faster on my little tiny microcontroller. I couldn't figure out why. Well, this was old and back in the day when little microcontrollers weren't quite as good as they were now, and they had voltage-dependent internal clocks. So they had a ring buffer that would ring around, and when my little energy harvester went in some weird state I hadn't considered, it was actually pushing voltage through this pin up here, raising the voltage of VDD of the entire chip, and then changing my clock frequency. And, you know, only 2 weeks of my life to figure that out. It was pretty cool. All right. They also have resistors in here. Why do they have resistors? Why would anybody want to have resistors?
Just so what you just described doesn't happen?
That would actually have been an easier fix. That's not inherently a reason why. Well, I guess I asked the wrong question. So here I'll tell you why there are resistors, why you'd want resistors at all, and that is for some communication protocols we talk about later, you can have it pull up on its own without having digital logic to do it. The trick is, why would this company choose to put resistors, which are physically large, on chip? Physically large resistors mean lower profit margins because you have more silicon. So why would a manufacturer put resistors on chip that somebody could put outside the chip?
Tampering?
For tampering?
Tampering or potential damage?
Well, that's not actually too bad. That's true. This thing is likely to exist all the time. That's you know, it's not like somebody's going to bump it off. It's because PCB manufacturers, like Apple, whoever who makes products, they're so size constrained that having a chip, a physical little resistor outside, is causing a problem now. Like, imagine your ear pods. They care about every little component that goes on there because it's so space constrained. So now it's a better profit margin in the sense that you put this in here and manufacturers will pay extra to have resistors internally because they're smaller than the actual like 0.001% of a penny that it actually costs to have a resistor outside your board. This economics point.
It might not be part of like
that's fine.
Class, but why can resistors be smaller on chip as opposed to off chip outside?
It's a good question. There's, I remember I was an electrical engineer once. I actually taped out chips at Intel and in other places. You can make really bad resistors using your diffusion, whatever, I forget what it is. There's a silicon way to make really bad resistors that are actually kind of small. And as long as you treat them right, they're okay. If you want really good resistors, they also take up more space. Either way, you're taking up space. What was your question? Sorry.
Yeah, why is it easier to have like smaller resistors on chip as opposed to like out of chip?
Oh, what's it's why? It's just a cost factor because they want small PCBs. So they're saying, okay, I rather pay more to have a more expensive chip just so I don't have to have a resistor outside my chip on my PCB. Yeah.
Wait, so the voltage of the output pin is gonna be in between ground and VDD?
I hope so.
Okay, and like if the two resistors were the same, it would be like precisely 1/2 of VDD?
Yeah, I usually don't turn them on at the same time. I don't even know if you can. But you could do that. You can imagine circuits where you might want that. There's actually, some of these GPIO pins actually have op amps as an alternative function, because they're like, well, having an op amp on my PCB is too expensive in terms of board real estate, so put it in this piece of silicon. There's all these sorts of trade-offs there are people making about trying to put things in. Okay. What did I want to tell you? I think I told you most of these things. Yeah, I clearly got off. Oh, wait. Yeah, and you probably know some of these things. So we have GPIO mode or motor register, right? And so it was actually not 1 bit, it was two bits. So you could do input, output, alternative function, or analog. Right? So you might look through the data sheet and see those as options. That's because you might want to have your I2C go through here, or you might want to be able to sample an analog pin, that pin through your analog path. And so where is this? Oh. You also have your clock enable bit. So I bet you've been going through and changing your clocks. You can set it to port B, you can enable it or disable it. It's a cost saving or power savings thing. And really, is this a GPIO pin and the AND gate? You're either raising this high or low. And having a clock run, especially like on modern processors, your clock, like on an Intel processor, the process is so leaky now that having your clock on is almost the same as having your flip-flops moving, right? Just because of how much power these things consume. So by turning off your clock, it's actually a pretty big power savings for that peripheral. That's why it's off by default, yeah.
So to read it in analog, I would assume you would like need to pass it through an analog to digital.
Yep.
So you would want to read like more than 1 bit.
This is just controlling. Yeah, this is just controlling that. I think there's a slide on the analog path back, but it would go to like an ADC or something.
But like if you were reading digital, you would only be reading 1 bit.
Correct.
With analog, are you reading more than 1 bit?
Correct. So we have a whole unit on analog to digital converters. So an analog to digital converter is a way to get the outside, that soft human world into this digital world. And so it's a device that will measure the voltage between 2 points, VDD and ground, let's say, and tell you what the digital representation of that voltage is. Let's see. Let's see. Oh, those are motor pins. Okay. The general purpose mode, sure. And this is the logic to get that done. Let's see. You can have your output type. So there's push-pull. That's the one you're probably most familiar with. So this push-pull means you're either going to connect, either VCC is going to drive through this pin and raise, this gate is going to be closed and raise this pin high, or it's going to connect this pin to ground and allow current to come back in. We had some Falstad circuit diagrams on the first day, I believe, that you can look through and see how this control thing works. The other modality that you might want is, I got ahead of myself again. The other modality you might want is to have an open drain. So open drain is there's nothing connected up here. They've disconnected the PMOS, and now this can either hold the pin low or let it float. So if this thing is open, if you had a switch here that was open, this isn't connected to anything. And the resistance here should be relatively high, say 100 kilo ohms or so. And so no current should be able to pass into here, and now you can let this thing float high, and or float to whatever value it's going to float to. And that's particularly useful for certain types of interfaces, certain types of sensors, but mostly it's useful for I2C, which is a communication protocol we talked about earlier. Yeah.
Okay, so open drain is low or high impedance?
It's either conducting current, so it's either it will result in a logical low, or it will be high impedance. You could have, so this is open drain, so the reason it's called open drain is that on the MOSFET or NMOS you have drain, source, and gate, and then if you have PMOS you still have source, drain, and gate. So you can have open collector or open source for a PMOS. You also have a number of different speed options for your GPIO pins where you can tell it essentially by writing into this speed address, right? So you'd set in these different pins. So here we're just showing, these are the registers that they're concatenated up in that, remember over here we're talking about green, purple, orange registers. This is just another register that wasn't in that diagram, which controls how fast the pins will go up and down. And then it's showing you, let's see if I can read this correctly. So here's the 0th pin up to the 15th pin, and then taking 2 bits. So the data sheet is saying this is a read-write, and this is the order 0, 1, this is the concatenation. 4th is 15th bit here, 16th bit pin in this register, or that peripheral. Why would you want to have different speeds for your GPIO pins? What does different speeds even mean?
The frequency in which you'd be receiving data.
Well, this is for drive strength. This is all about driving. Anybody else know why you'd want to control? Yeah.
Power consumption. So if you like, what you want to use like high, you can't afford high power.
That's a good one. It's also about, so it's drive strength is basically how much current you're going to use to push through this. So it definitely has a power impact. The other one is you don't always want to go really fast. It's not shown in the diagram, but you'll have ringing. So this is when you go up really high and it'll overshoot and it'll ring a lot and you'll add extra noise to your system if you're going too fast. Probably not an issue here. You guys, medium or fast are probably fine for any of the projects you're going to do. But if you really wanted a high bandwidth data line, and as a circuit designer, you're going to be responsible for ensuring there weren't overshoots by properly loading the end of the transmission line, then using high makes sense. Let's see. Oh, your output data register. Again, these are screenshots from your data sheet. And so here's pin 2, let's say, and pin 2 is connected, right, to an output of your GPIO pin when selected, and then you can read and write out of that pin. All right, what else do we have in here? Oh, and here's the alternate function we talked about. So here, if this alternate function was chosen, it's not really showing you the control bit for this, but it should go up to here. And then you can take your analog signal back. This buffer here, this is a Schmidt trigger. This is going to take a variable analog signal and turn it, or digital signal, and turn it into a nice clean state. And that can go to your alternate function or to your GPIO pins. Yeah, that's what I want to say. And then there's your output registers. We already talked about that, push up, pull down, different logics for those. Let's see. So Schmidt triggers, over voltage protection, that's great. Schmidt triggers. So digital signals are not always 1s and 0s, sometimes they're noisy. There's lots of places you get noise in from your system. A big one you get noise from is digital communication lines. Your power supply can inject noise at certain frequencies. So there's lots of places to get noise in. And so what a Schmidt trigger does, well, the normal, like a logical gate, would just go and say, anytime you're over VDD over 2, over this threshold, right, I'm going to go higher, low, higher, low, higher, low. But that may not actually represent your data. So a Schmidt trigger's goal is to add some hysteresis, which means, what's hysteresis derived from? Like the history of the previous state. And basically what it says is when you're transitioning from, say, low to high, I've got to go a little bit over VDD over 2 to make that state, and then I have to come a little bit under VDD over 2 to go to the back state. So here, I haven't gone high enough and it doesn't count. And then I went really high here. I made a full transition out of the state here. That went high, and then I made a full transition down. But these weren't significant enough. So you can imagine this is a cleaned up version of this signal. This signal is a cleaned up version of this signal. And it's important to know that these things exist because this is a typical, like, say this is a debouncing circuit, or this is some logical gate that, I don't know, some circuit you made where maybe it's a sensor that turns on when you have a distance sensor or something. And now all these little spikes occurred. This is an oscilloscope plot. You don't want anything to be triggered off these little spikes. You want it to know when exactly your data was here. So that Schmidt trigger is a tool to clean up logical edges. And all that exists inside your GPIO peripheral, and one for every, one of these parts for every pin, and there's multiple, and then the registers live here. What questions do we have about GPIO pins? Zero questions.
I just have a question, so like for like the pull up, pull down, when you're controlling those, is like the address of those like stored somewhere in memory as well?
Yeah, there's a control register for it.
Gotcha, okay. So
Right,
like
so
inside of that thing, there's a register that says like whether it's.
Yeah, it's not shown here, it's shown in the data sheet, but there's another little register here, and then we didn't show every single line that goes over here.
But there's things going to
Yeah, so the only way you can control things is basically through a register. And you're gonna do it through loads and stores from your core, and then every piece of functionality is available to you. You just have to read through the data sheet and be like, okay, that's the register I need to use to make this function happen. So a lot of what happens is, we try and teach you enough to read the data sheet, and then we just let you loose. Like, okay, it's in the data sheet. You wanna figure out how to make your I2C, or that communication bus that needs it, go high. Which register? I don't know. Look in the data sheet. As long as you know it's there. Yeah?
So are all GPIO pins capable of analog? I've seen some like boards that like say, oh, only this pin is like for analog. So like, is that like do you have to like support it on the board too?
So there's no laws or requirements here, okay? So each manufacturer can choose to do different things. So some manufacturers, let's say like, okay, only port, say A or port 1 can have analog function. That's just because in that peripheral, that's the only place they put the analog functionality, right? You know, there's no requirement that they have every GPIO pin has analog functionality.
Oh, okay.
Yeah. Okay. All right, so let's go through another example here. So hey, we're trying to connect to our GPIO pins. Let's see, so here, I guess these should really be, should be the, we're the requester now. But the requester's here, we have a target, and then these are our control lines back and forth to the GPIO pin, and your job is to go through and connect all these. Connect all the data lines such that this thing will be able to read and write out of those addresses, right? And when you make your mask, you can just write the address down so I don't have to look at bubble logic. Look through here, and this is telling you, this is what you would see like an exam or in a data sheet where it says, here's your GPIO out register. It is 32 bits. However, the top is reserved. Right? And then it's going to say those are read only. The top here is reserved, read and write, and then you have a mode configure. It tells you what the default is, it tells you what the address is, and it tells you what the pin functions do. And then you can look through, I just put this here so you guys can remember what the functionality of those things are. So when you work together, I have extra sheets. You guys try to wire the whole thing up. Sheet? No. Did I just forget you guys? That was like, oh, it was a lot.
He's giving this. No, it's not. This is like the sheet. He was like all of them. I know this. Put a clock. That sheet.
GPIO target on the previous slide is this.
Right means it's in output mode.
Control inputs are going to go into that target.
Wait, do you need to connect any of this?
What if you mode is set to input? That's invalid, right?
Did you? I really wanted you to do that number 4.
Yeah.
Do we care, or like, do we have to handle that? Not care.
No, I think we're overthinking.
I did the same thing to you.
Address?
Thank you.
Going to all of them in ODR and motor.
Register goes to.
We read data, read from the GPIO in, right? I don't know. Because
For the address, yeah.
This is like cleans up analog signals. Very old.
When? Where are we putting?
GPIO in, it's bias, no?
You can both of them?
From here to here.
But it's in So if the 4 is true in binary, that means you have a 1 in position, 3?
Oh wait.
So then you have
8 is 1, 0, 0, 0.
Just make a big and.
So the read data wrote here with the output, right? So in this case, would you say like you're in?
But that's the GPIO isn't always high. I guess it doesn't really matter.
These addresses, do they all go into 1?
You can just keep it always enabled. Even if it's right, you don't work.
Yeah,
Listen anyway.
They all end with the P write, enable, and P select. Wait.
Like so it'd be this.
You have to distinguish it out.
We still want it.
I just matter this time. Yeah.
So we have like a
Can I
math
just
and.
do the math thing right? Like if I just label like
We'll just put it up top.
Goes to here.
So would we have like
There's a control here.
massive AND gate that takes in these 3 addresses and these 3 wires, and then it goes into the.
Yeah, you need probably need a NAND gate for those, and then yeah.
Oh, and then connect to 1. Okay.
Another one. Many ways to do this.
Right.
And then you would.
Now we enable. How do we do that address map?
So you take the, I concatenated the first 4 bits right?
Oh, that goes to data.
Ready.
But what bit?
First.
And then we get
So it goes to data, right?
Yeah.
Go to enable.
You just need to
You go to enable.
should be right here.
Never worked with persons too. That's what it says here, like. So they would just do the same.
First 8
I got it. He's sending that data.
It'll represent 8.
I'm doing these first.
Oh, you're making it to 3 and.
I'm gonna do.
Yeah, right in the brackets. I think so. Yeah.
I'll try to do 20.
Where are you gonna drive it?
I think so. It's a lot easier to do in level up.
But it just. Your data is a 31 bit, so we're gonna take all of it.
Give up.
Is that adder or address?
The secret we didn't really.
Enable's on the bottom, and one of them's already wired to be ready.
You just fucking.
Wired to be ready.
Register, right?
I guess I told you. That's
So
what
this one is.
I think they just go to the enable,
This here.
but I'm not entirely
You only have a
sure.
right to that out. Just loading them. Isn't that what you're
Using this adder mask could go.
Like immediately.
I didn't know what was happening.
So if it's going in.
You're in Monday nights, didn't know what's happening.
Which one we write to based on like
What do we use in front of lab?
like 400.
I put in my
No.
So
it was just memory mapping.
For the enable of these
I'm talking about like these control signals, but on the general scale.
it's together for if we actually were to
You still
do
doing
it.
this stuff.
No, this is like the application of the control signals that we talked about.
So for the
These increase by
but I don't want to be that litigious.
So the one thing I did out was like that
Sending.
would be the incomplete.
yeah, whatever bit it is between these two.
Yeah, and it's
Can I read out of this register?
the lower.
But if I'm a core, right, and I want to read, what's the pin?
You would read out of this, but you would.
I did fall
They're amazing children's drawings. You're in lab, and you're like, what's the state of my mode?
And where does how do you split the data?
Yeah, cause like I don't know that.
Up by 4 bits.
then you connect it with the enable.
Then you add it, right?
And then for the mode.
And then ODR goes to
Once it starts going over.
And then add it with the enable.
Yeah, with this stuff, yeah. But for the data line, odor controls the.
Because there's 16 pixels.
Do you need marks to select between whether or not you're writing to mode?
No, we just don't enable one.
Whichever way you want. You could have done there, not be bothered.
My question is, do we need it ready?
Yeah, this is bullshit too. And I have no idea.
I don't know where you get it from, so I'm gonna just say no.
I don't know, man.
Has its own address.
The marks for the right sweep data, whatever stuff.
Written through the.
Or default form, so I think it would be fine if you could define because it will just update the clock cycle.
Send my data to all. The data does go to all.
Cycle updates,
Clock will actually allow data to change the clock. So I can enable this when that is.
I think order is
Use it to is constantly enabled.
Choose which one you're reading from.
Feed it into GPIO because there's
like output. Yeah, that makes more sense. Through the control thing.
Always update. Every clock cycle is clocking in data on data.
0, 0, 0. Draw the address.
Or cannot manipulate that.
The key data is going.
No write functionality.
Well, that's
you got all the tricks. It's very hard to do it.
actually shows good.
Plays after this. Yeah, I think it's Zane's there. Zane's there. That's why. 42. We have 42 after that. I haven't watched one of his lectures. Zane was like, I'm not coming to today's lecture because I'm one lecture behind. So I was like, if you're not going to be
If you have the selector, right, then like you can send data everything.
I want to be.
You and that with the address.
This memory address. Allow the core to read for that memory address. Right now you said you can't.
Yeah, it doesn't matter. You just put in read from data
this line. So let's get that file.
Like, I guess
All the key shit.
The biggest thing is, I just might need a must and switch just one of these.
How are we connecting that? With a model?
I see. How does this thing get data?
I guess.
That's the part that.
This one is currently.
Oh yeah, it does. It's not.
I guess that one to the lighter side.
Every clock cycle, it's gonna.
Or like right here. That's like this.
Always choose anything.
Get this address, just make sure that
Oh, so there needs to be another AND gate? Yeah, you're right. There needs to be another AND gate.
What do you guys do with the address?
It should.
Use this part. Okay, I just thought that was another diagram. That makes sense.
No, it's part of it. It's part of your diagram.
Okay.
Goes into one of the fits.
What are you doing so far?
Why did I take this class?
There's got like 3.
That's what I'm saying. I'm surprised. The fact you found this.
Already unreadable.
Now, I'm gonna tell you.
That's just fine.
It's just fun.
I'm gonna try this one.
So that's why we're selecting.
I don't have a good idea to say anything.
Better than my solution. You guys are all smarter than me. If it's one of these two bits, it's going to either enable this, right, which is going to allow data to get written in and clocked in, or it's going to do this one, and then when it's done with those two things, it's going to not do anything. All right, great.
Let's try saving for me.
I don't know what you're doing.
Looks like a not game.
It was like 5 days.
I think that request really
Wait, can I see this?
That makes sense.
That'd be a dick.
Motor definitely sends it to the controller. So does the guy.
I have no space. It's just like that.
Motor just goes into control, right?
Yeah.
It was always high.
And high.
Oh, we only got 2 minutes.
Input to the flip flop.
All right, let's go through and finish this off. All right, so remember, these are registers in your peripheral. This whole thing is a peripheral. It is a completer. And your job is to make the combinational logic here such that this achieves the goal of being able to write in, let's see, those are the addresses which this thing should be write in data, this thing should be write in data, and they should all read out. This one you don't write data into. Where does that data come from? Oh, well, it comes from over here. We'll get to that. I forgot which order my bills go into. So you're able to write data into here, right? So you got 32 bits coming here. If you look back at the data sheet above, it said that these two were read or write. So you can read and write data in. So that's going to go through that path. Now, data, you could read data from all of them. So all 32 bits are going to come back. The problem is the lines would collide, right? You can't have all those buses go into here, have to switch between them. So we're going to put a mux up here. So that mux is allow you to choose which one of these registers is connected back to the bus, back to the requester. And then we're going to take the 32 bits out of that. P clock, there you go, goes to everything. Now we're going to get to the and, the masks. Why do we want to have these? Well, they have different functionalities. Different things should happen depending on the address. So this should only latch new data in from PWrite data when that address, POut address, is instantiated on this address line. So we're going to use a masking function to mask for that. And I didn't write it out. I just said, here's what it is. Could have written it out in the binary or some other way. But I'm going to take all 32 bins in here. Now, somebody back there had a more clever solution to me. They only looked at like the second bit there, and that was all they needed to do. That's a good solution too. All right, so now one of these things will go high when it's required. And you got your and, so it has to be PWrite, PEnable, and PSelect have to be true. And then we're gonna and all that together through some horrible logic here. So let's see, when you have the correct address and your PWrite, PEnable, PSelect, only then will this thing be enabled and be able to clock in PWrite data in from D into Q. And what else we got? We got this one, where does it get its data from? Well, this is a read only, because you can't write data from the core into a GPIO input. That has to come from the pin itself. So this comes in this way and will automatically update. I had an error on your sheets which showed this thing was always on. So this was always clocked. This was pulled high. So this clocks every clock cycle. It's going to take the data from here and put it there. Okay, what else? What just changed? Oh, I did that, okay. And then this is always ready, right? Oh, and then the control register here is connected. And then I just chose, I didn't tell you guys, I didn't give you guys a full prompt, but I just chose that the 0th bit is the one that's actually controlling this particular GPIO pin. So I took the output 0th bit of here and the control register here. There you go. What questions do you have? Oh, lots of questions, yes.
Why does the mux need 3 selector bits? Only like 3.
Why does the bus, which bus?
The mux.
Why does the mux need, I just did one hot encoding, I don't know, I was lazy. I was lazy professor. Yeah.
So what's like the difference between the select and the enable? Was ANDed together.
The select and enable, the select selects one of the 64 or N peripherals you have on your device. Enable tells it that the data is instantiated and ready. Now, it could be, so those are two different functions, and if you get more complicated peripherals, you actually may need to give it some wait time or some other task, so that's why they say there's an instantiation phase. I call it the setup phase. More questions? You want to leave? You want to leave more than you want to learn? No. Bonus points. Okay. All right, I'll see you guys next week.